Hello everyone, my name is Buğra Bayram. I'm studying mechanical engineering at Ege University. I made this video to understand the relation between the carbon and nanotechnology. I hope you will like it. So, here's an overview to see topics and what we're gonna talk about exactly. First, I will try to explain you what's nanotechnology and what is carbon also. Then I prepared some slides about the relation between carbon and nanotechnology in history. Also, you will hear the names of some sites who make some studying about nanotechnology. And then I will talk about the types of carbon nanomaterials like Fullerenes, carbon nanotubes, carbon nanofibers, and graphene. You will also see what's the structure, history, application, and advantages and disadvantages of them. So let's start. Nanotechnology is science, engineering, and technology conducted at the nanoscale, which is about 1 to 100 nanometers. Nanoscience and nanotechnology are the study and application of extremely small things and can be used across all the other science fields such as chemistry, biology, physics, material science, and engineering. Carbon is a chemical element with the symbol C and atomic number 6. It is nonmetallic and tetravalent, making 4 electrons available to form covalent chemical bonds. Carbon is the fourth most abundant element in the universe by mass after hydrogen, helium, and oxygen. Carbon's abundance, its unique diversity of organic compounds, and its unusual ability to form polymers at the temperatures commonly encountered on Earth enables this element to serve as a common element of all known life. It is the second most abundant element in the human body by mass after oxygen. Thousands of years later, in the 11th and 13th centuries, the Crusaders encountered unusually strong and sharp sword blades when they fought against Muslims. Part of the reason for the exceptional strength, remarkable sharpness, and beautiful patterns on the surface of the Damascus steel sword blades used by Saladin's troops may have been the presence of carbon nanotubes in the steel used. Scientists looking at such sword blades under the electron microscope have seen evidence of carbon nanotubes in Damascus steel. And maybe this is the first time using the carbon and nanotechnology together in the world history. Fast forward 800 years to 1985, Richard Smalley, a professor of chemistry, physics, and astronomy at Rice University, found remarkably stable clusters of 60 carbon atoms were produced when he shot a laser at a sheet of graphite. These clusters look something like a soccer ball or the geodesic domes designs by Richard Buckminster, Bucky Fuller, and are called Fullerenes or buckyballs. Within a few years, Smalley and other scientists had discovered a whole host of variations on the Fullerene theme including carbon nanotubes. Smalley and others also learned how to make relatively large quantities of these nanomaterials. Some of these structures were later shown to occur in nature and to be produced when we burn things. In 1996, Smalley and two colleagues received the Nobel Prize in Chemistry for their discovery of fullerenes as a new form of carbon. Fullerenes. Spherical fullerenes are sometimes called buckyballs. The C60 variant is often compared to a typical white and black soccer football. Cylindrical fullerenes are called bucket tubes. Recently discovered is the Bucky-X by researchers at UC Davis. Fullerenes are similar in the structure to graphite, which is composed of a sheet of linked hexagonal rings, but they contain pentagonal rings that prevent that sheet from being planar. History of Fullerenes. In 1985, Harold Kroto of the University of Sussex, working with James Heath, Sean O'Brien, Robert Charles, and Richard Smalley from the Rice University, discovered fullerenes in the sooty residue created by vaporizing carbon in a helium atmosphere. In the mass spectrum of the product, discrete peaks appeared corresponding to molecules with the exact mass of 60 or 70 or more carbon atoms, namely C60 and C80. The team identified their structure as the now familiar buckyballs. Structure of fullerenes. Fullerenes are molecules composed entirely of carbon, taking the form of a hollow sphere, ellipsoid, tube or ring. The molecule was named for Richard Buckminster Fuller, a noted architect who created the geodesic dome. Since Buckminster fullerenes have a similar shape to that sort of dome, that name was thought appropriate. The structure of C6C is that of a truncated icosahedron which resembles of a football of the type made of hexagons and pentagons, with a carbon atom at the corners of each hexagon and a bond along each edge. Application of fullerenes. Fullerenes have been extensively used for several biomedical applications, including the design of high-performance mRNA construct agents, X-ray imaging contrast agents, photodynamic therapy, and drug and gene delivery, summarized in several comprehensive reviews. Medical research. In April 2003, fullerenes were under study for potential medical use, binding specific antibiotics to the structure to target resistant bacteria and even target certain cancer cells such as melanoma. The October 2005 issue of Chemistry and Biology contained an article describing the use of fullerenes as light-activated antimicrobial agents. Carbon nanotubes. Carbon nanotubes are cylindrical molecules that consist of rolled-up sheets of single-layer carbon atoms. They can be single-walled with a diameter of less than 1 nanometer or multi-walled consisting of several concentrically interlinked nanotubes, with diameters reaching more than 100 nanometers. Their length can reach several micrometers or even millimeters. The rolling up direction of the graphene layers determines the electrical properties of the nanotubes. Charlotte describes the angle of the nanotube's hexagonal carbon atom lattice. Apart from their electrical properties, which they inherit from graphene, carbon nanotubes also have unique thermal and mechanical properties that make them intriguing for the development of new materials. Their mechanical tensile strength can be 400 times that of steel. They are very lightweight. Their density is one-sixth of that of steel. Their thermal conductivity is better than that of diamond. They have a very aspect ratio greater than 1000. Just like graphite, they are highly chemically stable and resist virtually any chemical impact unless they are simultaneously exposed to high temperature and oxygen, a property that makes them extremely resistant to corrosion. History of carbon nanotubes. In 1991, following the discovery and confirmation of the Fullerenes, Sumio Aijima of NEC noticed multi-wall nanotubes developed in a carbon arc discharge, and after 2 years, he and Donald Bethune at IBM independently observed tubes, that is, single-wall nanotubes. These pure carbon polymers could now be inferred in the perspective of Fullerenes, transforming one's perception of them to molecules, with all that unique designation implies. At present, after 10 years of Aijima's initial observations, considerable details about nanotubes and tubular Fullerenes have been known. It is known that multiple nanotubes are consistently made with a high frequency of structural defects. Structure of carbon nanotubes. The structure of a carbon nanotube is formed by a layer of carbon atoms that are bonded together in a hexagonal mesh. This one-atom thick layer of carbon is called graphene, and is wrapped in the shape of a cylinder and bonded together to form a carbon nanotube. Nanotubes can have a single outer wall of carbon, or they can be made of multiple walls. Carbon nanotubes have a range of electric, thermal, and structural properties that can change based on the physical design of the nanotube. Now we're gonna see the two types of carbon nanotubes: single-wall carbon nanotubes and multiple-wall carbon nanotubes. Single-wall carbon nanotubes. Single-wall carbon nanotubes can be considered as a single long wrapped graphene sheet. Nanotubes generally have a length-to-diameter ratio of about 1000 and hence considering nearly one-dimensional structures. Single-wall carbon nanotubes generally have a diameter close to 1 nanometer and are multiple thousand times longer in length. Single-wall carbon nanotubes possess distinct electronic properties when compared to multi-wall carbon nanotubes, nanotube variants, which make them most suitable candidate for miniaturizing electronics to replace the micro-electromechanical systems that are currently the basis of modern electronics. Multiple-wall carbon nanotubes. Multiple-wall carbon nanotubes consist of multiple carbon nanotubes nested within another. The number of nanotubes that are within a multi-wall carbon nanotubes can vary from as little as 3 to over 20. At the same time, the diameter of both the internal nanotube and the external-most nanotube can vary from 2 nanometer for the innermost tube to over 50 nanometer for the outer wall. Just like single-wall nanotubes, they exhibit exceptional electrical, thermal, and mechanical properties. However, due to the increased number of walls, there is a higher likelihood of defects being present compared to single-wall nanotubes, resulting in reduced performances. Application of carbon nanotubes. Carbon nanotubes have been making quite an impression on commercial products for some time now. Carbon nanotubes are already being used to control or enhance conductivity in polymers and are added to anti-static packaging. The most popular current use for carbon nanotubes is structural reinforcements. They are added to other materials like rebar to constraint because of their high strength, low weight, and flexibility. Carbon nanotube production is also used in bulk composite materials and thin films. Multi-volt nanotubes were first used as electrically conductive fillers in plastics. Today they are also used to enhance fiber composites. Examples include wind turbine blades and hulls for maritime security boats. By 2005, 50% of lithium batteries incorporated carbon nanofibers, which are wires spun from carbon nanotubes. Carbon nanotubes are even being used to enhance sporting goods like tennis rackets, baseball bats, and bicycle frames. Carbon nanotubes in medicine. Carbon nanotubes are even emerging in the medical field. Spanish researchers have created a biosensor that can diagnose yeast infections quicker than the current method. When the transistor containing carbon nanotubes and antibodies programmed to attack the candidate yeast cells is put in contact with a cell sample. The interaction between the yeast and the antibody changes the electric current of the device. Advantages and disadvantages. Advantages: extremely small and lightweight, making excellent replacements for metallic wires. Resources required to produce them are plentiful and many can be made with only a small amount of material. They are resistant to temperature change, meaning function almost just as well as in extreme cold as they do in extreme heat. Improve conductive mechanical properties of composites. Disadvantages: despite all researchers still don't understand how carbon nanotubes work. Extremely small, so are difficult to work with. Currently the process is relatively expensive to produce the nanotubes. Would be expensive to implement this new technology in and replace the older technology in all the places that we could. At the rate of technology has been becoming obsolete, it may be a gamble to bet on this technology. Carbon nanofibers. Carbon nanofibers are cylindrical nanostructures with graphene layers arranged as stacked cones, cups, or plates. Carbon nanofibers with graphene layers wrapped into perfect cylinders are called carbon nanotubes. Carbon nanofibers are Sp2-based linear, non-continuous filaments that are different from carbon fibers, which are continuous with diameter of several micrometers. History of carbon nanofibers. The first electron microscopy observation of carbon nanofibers were performed in the early 1950s by the Soviet scientists Radushkevich and Lukyanovich, who published a paper in the Soviet Journal of Physical Chemistry showing holographic carbon fibers that are 50 nanometers in diameter. Early in the 1970s, Japanese researchers Marinobu Endo, now the director of the Institute Carbon Science and Technology at Shinshu University, reported the discovery of carbon nanofibers, including that some were shaped as hollow tubes. He also succeeded in the manufacturing of VGCF with a diameter of 1 nanometer and length of above 1 millimeter. Later, in the early 1980s, Tibet in the USA and Benicet in France continued to perfect the VGSF fabrication process. Application of carbon nanofibers. Lithium-ion batteries, field electron emission source, composite materials, scanning probe, microscopy tips. Carrier material for various catalysts in petrochemistry. In vertically aligned arrays, a platform for gene delivery. For electrode materials. Oil spill remediation. Graphene. Graphene is the name for an atomtic honeycombed sheet of carbon atoms. It is the building block for other graphitic materials. Harder than diamond yet more than elastic than rubber. Tougher than steel yet lighter than aluminum. Graphene is the strongest known material. To put this in perspective, if a sheet of cling film had the same strength as a pristine monolayer of graphene, it would require the force exerted by a mass of 2,000 kilograms or a large car to puncture it with a pencil. Graphene possesses other amazing characteristics. Its high electron mobility is 100 times faster than silicon. It conducts heat 2 times better than diamond. Its electrical conductivity is 13 times better than copper. It absorbs only 2.3% of reflecting light. History of graphene. Although sporadic attempts to study graphene can be traced back to 1859, there has been an explosion in research around the material since 2004, when Professor Sir Andre Jain and Professor Sir Kostya Novoselov of the University of Manchester discovered and isolated a single atomic layer carbon for the first time. The pair received the Nobel Prize in Physics in 2010 in recognition of their breakthrough. The Scotch-tape method used at Manchester was so simple and effective that this area of science grew extremely quickly, and now hundreds of laboratories around the world deal with different aspects of graphene research. Structure of graphene. Graphene is a two-dimensional carbon electrode. It's composed of carbon atoms positioned in a hexagonal design, which can be said to resemble a chicken wire. In graphene, each carbon atom is covalently bonded to three other carbon atoms. Thanks to the strength of the covalent bonds between carbon atoms, graphene boasts great stability and a very high tensile strength. Since graphene is flat, every atom is on the surface and is accessible from both sides, so there is more interaction with surrounding molecules. Application of graphene: biological engineering, optical electronics, ultrafiltration, composite materials, photovoltaic cells, energy storage, sensors. Advantages and disadvantages of graphene. Advantages are it's ultra-light and also immensely tough. It's 200 times stronger compared to steel and incredibly flexible. It's the thinnest material possible and it is completely transparent, which can transmit more than 90% of the light. It's the ultimate conductor and it can function as perfect barrier. The helium cannot even pass through the graphene. It can transfer electrons at much faster rate compared to silicon. It can pass at the speed of 1000 kilometers per second, which is about 30 times fast compared to silicon. Graphene can be used in most popular market of smartphones and wristwatches. It can be used in flexible electronic newspaper, foldable televisions. It can be used in clothing which use graphene-based photovoltaic cells, as well as superconductors. Due to this, tablets and mobile phones can be charged in minutes while in the pockets itself. It can be used for a wide variety of applications such as flexible displays, RAM, energy-efficient transistors, energy storage devices, textile electrodes, copper nanowires, thermal management, spintronics, and the others. Disadvantages: creation of high-quality graphene is expensive and complex process. In order to grow graphene, toxic chemicals are being used at high temperatures. Due to these it exhibits toxic qualities. It is susceptible to oxidative atmosphere. So here you can find some references that I used for create this video. Thanks for listening to me.